I'm from the Chemical Engineering and Material Science Department here at Minnesota. So I'm kind of a duck out of water to come and talk to an analytical group. It's quite fascinating to me to see the things you're working on are so advanced compared to what I'm going to actually show you probably. But I thought there would be some interest in kind of what we're doing and the problems we're after. The problems we're after come about from what we're really interested in, and I'm a reaction engineer and I work in the field of catalysis also. And the problems I'm interested in are like energy and chemical applications. So you can see here, one of the chemistries we spend almost all of our time focusing on is high temperature conversion of biopolymers for biofuels. And this chemistry takes place at about 500 degrees C. A solid material reacts within 1 to 2 seconds. It breaks apart into hundreds of compounds that are volatile. Then you quick quench it. You end up with this ugly liquid in the middle, which is analogous to petroleum. And then you would take this and then upgrade it to consumer products, fuels, chemicals, etc. So I'd love to spend all of my time just studying these chemistries right here up at the top. And the problem was when you start to do analysis of these types of systems, you end up working with gas chromatography chromatograms that look like this, right? And so that's your worst nightmare. So how do you deal with that? Well, for years we've spent enormous amount of effort trying to come up with identification for all these compounds, which is actually the easier of the two problems. If you couple this with mass spectrometry, you can do a pretty good identification for about 90% of the compounds. And after that, you have to get a little more creative, but you can do it. What is really a problem is if you start to look at what the compounds are, they're quite oxygenated and oxidized. So you see a lot of double bonds, a lot of oxygen. And that means that your response on a conventional flame ionization detector is very unpredictable. It can be an order of magnitude different between two molecules you think would respond the exact same way. So how do you get good quantitation of these types of complex mixtures, especially when you're dealing with 200 compounds at the exact same time? So like I said, I wanted to work a lot on the chemistry. We ended up becoming just analytical worker bees for hours and hours and hours. And that was sucking up all the productivity and a lot of cost buying standards just so we could inject them and try to calibrate. And so we started thinking about other problems too, right? We're not the only ones with this problem. This is another classic chemical process that's been in development for decades called methanol-to-gasoline, or MTG if you know it. In this case, you take methanol, you use a solid acid catalyst, zeolite material, aluminum substituted. You'll make hydrocarbons, oxygenates, gasoline type molecules. And depending on how you operate, you'll make a broad distribution of different compounds. And you can see that here, right? The people working on this is work from Enrique Iglesias at the University of California, Berkeley. Right, they have the exact same problem. You can see a little bit more grouping here with the molecules. But again, the FID signal over here on the left, wide variation of compounds depending on what you're working with. But there's, again, too many compounds, time-consuming analysis. If you buy standards, they degrade and they cost a lot. And on top of that, some of the compounds are virtually invisible. Some just don't respond in FID, and some have such a low response you can't see them. So, but there is some grouping here. So you can start to see C1's dimethyl ether just from the dehydration of methanol. And then you'll start to see the alkylation chemistries that will produce all of the larger hydrocarbons. So what's the problem, right? So if you use a conventional detector with a gas chromatography column, once you do all the separation, right, you design your column, you'll start to see the analytes elute one by one. They'll be injected into this hydrogen flame, and then you'll start to form ions, which are then detectable, hence the name flame ionization detector. And the problem is that different types of analytes produce different fractions of ions, and then those ions give a different response, and that's what we calibrate for when we do these calibration curves, right? So here's 9 different compounds, right? Some respond very nicely, some almost not at all, some are half, right? So it's very different in terms of sensitivity. So how do we go about improving this type of system? And the idea is very simple, right? Could we take whatever molecule analyte we're working with, put it through some sort of inline catalytic reactor, convert everything to the exact same compound, in this case methane, and then just run methane through your FID, right? Because then every species has the same response because it is the same species, right? And then of course, right, all those 9 compounds would all look the same in terms of quantification. So incredibly simple concept, right? So how do we do this? This is the device we've been working on for the past year. It's called the quantitative carbon detector. And the company's here that's actually taken this and taken it way beyond what we could do in our research laboratory. I'll say more about that in a minute. So going forward, you can see all of the species we were just talking about, but then if we overlay the comparison between a conventional flame ionization detector in black and the polyarc, this is the quantitative carbon detector trademark name of the company, you can actually see a couple things. One is that you get very nice resolution of the species. So we've made the chromatogram a little darker in blue here so you can see it, but you retain the resolution that you get from all that chromatography you've done up and which has been optimized for separation. But the other thing that's really neat is you can see other things. So you couldn't see CO2 before. Now you can see that peak because it's been methanated, right? That's not a new thing. We've seen methanators before on chromatography systems. But you can see other species that were very difficult to see with a flame ionization detector, such as formaldehyde, formic acid, and other highly oxidized compounds like that. Lots of time. So that's very useful. And there's a lot of other species like this that have very low response or almost no response that are now visible in these types of systems. And for the carbohydrates that we work with, there's a lot of those. So going forward, you can look at lots of alkanes. So one of the things you can do is look at series of molecules very simply. So if you do an injection of linear alkanes, in this case, you can see all of the species. They all have the same amount, so they have the same surface area. So if you were to integrate these, it'd be all the same. They give you a nice relative response factor that's all about 1, and with very low error, so about 1%. And if we do a side-by-side comparison, the error is about double by conventional, even if we're extremely meticulous in our calibration. The benefit of not having to calibrate reduces a lot of error in all the extra steps you have to go through. So how do you do this? Like I said, the chemistry is conceptually simple, but to actually implement the device involves all sorts of extra things that you'd have to think about to actually implement the chemistry the way you'd want it to occur. So from the column, you have some analyte goes into a combustion chamber, mixed with air. This comes out, and then this reacts over a second catalytic chamber, mixing with hydrogen. And then this whole system of flows, mixing, catalyst selection is designed to give you greater than 99.9% conversion to methane, which then goes to your FID. So how you do this, this is the actual commercial device. It doesn't look anything like what my students and I came up with when we did our own machining and swage locking and everything, which is very ugly. It's a much more elegant system that has capillary chambers, which is quite important for mixing. I'm not going to actually show you this is proprietary, what the flow system is on the inside. But again, it's very simple. You have some sort of oxidation chamber with a supported metal catalyst. And then you have a methanation chamber where this then flows into and mixes with hydrogen and then flows out to the FID. And the temperature of both of these is set in the entire block by a heating cartridge with a PID loop that integrates with your gas chromatography system. So in here, into this chamber is a built-in heater, and that heats the whole block such that it's isothermal. So one of the design challenges, your catalytic oxidation has to match the methanation temperature for this to be extremely simple. So how do you do all of these things and guarantee the 99.9% conversion to methane? Actually, that says conversation, but should say conversion, right? So how to do this? So you can just look at this. This is kind of a brute force method, right? So we'll say that we'll do these chemistries, but if we allow them to go to completion and achieve equilibrium, what would that be? So in this case, you can think about all of these systems together on a single plot, ternary plot, where we look at, for the mixture of your analyte, the carrier gas, etc., the hydrogen, oxygen, carbon, from everything mixed together, where would you sit on a plot that dictates the products at equilibrium? And there's a lot of information here. So here you can see the oxygen, the carbon, and the hydrogen. And you can see the line here. This is the combustion line. So to the left of this, you're either at stoichiometric combustion conditions or above. So for the first chamber to achieve high oxidation conditions, you want to have all of your analytes coming in be on the left-hand side. So you can see the gray here. Now the other part of this is that you want, when you add the hydrogen then in the second chamber, to have enough hydrogen that you'll push the equilibrium so far to methanation that all of the analytes that have been converted to CO2 go to methane. And so you can actually calculate those equilibrium lines as a function of temperature. Here's 200 degrees C, 300, 400. And obviously, as you go higher and higher temperature, this region of space gets lower and lower. So the optimization for the system is very simple, right? You want high enough temperature for fast kinetics to get the equilibrium, but you want low enough temperature that gives you a beneficial thermodynamics that you'll push everything to methane. So the actual design temperature is somewhere between 400 and 500. Now all the analytes I'll show you actually sit way up here in this tiny little corner. Here's a bunch of compounds over here. They scatter around actually in a relatively small space because we're overloading the reactor with oxygen and hydrogen. So in this space, everything, if the reactor is designed to go with a long enough residence time, should go completely to methane. So we can do this. Here's again, this is the device we've tested. If you look at the response factors for 15 different compounds, which are very hard to see, but there are things like carbon dioxide, methane, propylene, here's furfural, phenol, acetal, paraxylene, levoglucosan. Right? Again, I was showing you earlier, a lot of these compounds, the response factors are all over the place. And when we do the same analysis with the other detector combined with the QCD microreactor, you can actually see the response is equal to 1. So if you were to compare both methods side by side, you could get the exact same response between the FID approach or this approach, which we're claiming here. And you can see that with the parity plot. All quantification occurs on the exact same line. Now, one of the challenges here is, again, you put all this effort into your column design and chromatography to separate something that's 100 or 200 or 300 compounds to get really nice separation. So it'd be really a shame if you did that nice separation, then you remixed everything back in a reactor. That would defeat the whole point. So a big part of the design, when we were doing this crudely in the lab with our own machining, was to get the axial mixing down to a negligible amount. And actually, you can see that here. This is the old, really crude design where you can see the difference between a system without the reactor and systems with the reactor. So there's not much loss in chromatographic resolution. And now with the new capillary design, this is actually a 3D printed metal reactor that has capillary flows. You can't tell the difference, which is what I was showing you earlier in the side-by-side comparison. So this, what's been happening is then the integration with the GC the goal is to make this so you basically don't have to work with it at all. If it sits in a chamber, so here's the reactor, this then sits into this system right here, which is insulated and integrates with your GC such that you can have air flows and hydrogen flows, and the heating cartridge integrates with the controller on your GC system. So then the column, this sits right on top, the column comes out, goes into the reactor, it has its own heating system, goes back in and into the FID. And when you're using it, you don't really have to do anything, actually. So that's part of it. Other issues are how long will this last? So this design came about with the idea that even if you make this as robust as possible, selection of metals, contaminants, also those sorts of things, you definitely want a cartridge approach. So this little reactor here is cheap. The whole system is actually not that expensive, but you can change this out 6 months to a year time frame. But even so, this is an example done by the company that I'm copying here, where they've done almost 3,000 injections of the system to show that the response factor stays the same even when switching between all sorts of different compounds, alcohols, N-heptane, ethanol mixtures, etc. And actually the interesting thing here is when you start to do thousands of sequential injections, you'll start to see interesting things like if you have a sample bottle, you'll start to see small amounts of evaporation off the top of the out of the bottle will actually show up over hundreds of injections, and they have to switch the bottle and start over. Okay, what can we use this with? Obviously, carbon, oxygen, hydrogen work very well, but we'd like to go to even bigger heteroatoms. So things that are interesting are obviously things like nitrogen, sulfur. The benefit here being that those heteroatoms don't interact with the FID. So if they go through, they'll be oxidized, then reduced to species that won't interact with the FID, and they'll pass right through. And you can quantify the carbon without worrying about the heteroatoms, which for fuel mixtures is critical because there's so much sulfur and thiophenes and things like that in your fuel mixture. But other things that I'm interested in are also heavy. So something like terephthalic acid over here is quite heavy. And to study those, you have to do some sort of pre-preparation to actually analyze them. So I have a really great undergrad in my lab right now who's just putting the end couple of last finishing details on a paper. where we're looking at a whole range of materials that are very heavy that show up in consumer products. For example, this is a molecule called furan dicarboxylic acid. It's an alternative renewable chemical for terephthalic acid. So he's doing the trimethylsilylation of these species and then analyzing them with this polyarc QCD approach. Or other things like Tylenol, flavoring, food, pesticides. He's got a whole range of things we thought were interesting to people that we could look at, including taking things like actual consumer products and comparing with peer standards. So again, if you do this type of trimethylsilylation, you have the silicon. So the other heteroatoms, like sulfur and nitrogen, will pass through as a vapor, but silicon will actually form silica thermodynamically inside the combustion chamber. So our initial calculations here show that that is such a small amount of silicon that the silica you form would take thousands and thousands of injections before it accumulate to the point where it'd even be a problem. And so that we wanted to show that, first of all, but also that it wouldn't interfere with the chemistry. So here's the response for the conventional FID using the trimethylsilylation, and here's the response using the QCD. So you can do not only these light components and the heteroatoms, but also the heavy silica type species. So I'll leave it at that. I think there's still a few minutes for questions here. I apologize I didn't do the chalk talk approach. I didn't know the culture. I think somebody had told me and I forgot, and I was making my slides last night. So anyway, this is a really interesting conference, and thank you for listening. So.